Thank you so much. Welcome again today for microprocessor systems. The past lesson which we did, we talked about some instructions which are used in Intel 80/80/885 microprocessor. We saw different types of instructions, things like data manipulation, input-output transfer group, jump instructions, and also we used to do the data movement from one point to another. We tried to do some instructions like move immediate and some examples, MOV, the difference between move immediate and MOV. We tried to also to talk about add immediate and add A, and we tried to do some examples under what? Under those instructions, so that at least the candidate or anybody who wants to learn this can understand how we apply these instructions in programs. So today, basically we want to do more examples and more instructions, so that at least a candidate who is able to do this Intel 80/885 microprocessor is able to understand and write what? Write programs under Intel 885. Welcome so much. Let us continue. I want us to do the first example. And the first example is we want to write a program. So we say the question should be write a program to add 3E/F0H plus, let me put it here, plus 905H. H means hexadecimal, so we agreed under digital electronics. So now, our question wants us to add these two values, 3E/F0905A. I want to use two methods to do this program, because sometimes the examiner can ask you to add these two without using register pairs, or you can be told to use register pairs. So what I will be doing, so that we understand what we are doing here, we shall be writing the program, then we draw the trace table, so that we see what's happening in each program. I want to start with register pairs. When we use register pairs, how do we do this one? So what we do is, we use a register pair, HR, BC, and the DE. But when we use register pairs, as we saw in the last lesson, is HR becomes our accumulator, which means after addition of the two values, the 16-bit values, the result is stored in the register pair HR. So the first instruction will be RXI H, 30FEH. So it means data 30FE has gone to register pair HR. Though we are just seeing H here, whenever the microprocessor will see the instruction RXI-H, it knows that this is register pair HR. Then from there, I can use BC or DE. We can decide which one to use. For today, I've decided to use BC. So the next thing would be RXI B, what? 905AH. So these two instructions is like move immediate in registers. But for register pairs, we use what? RXI. So load register pair. That's the meaning of that instruction. Load register pair. Which one? HR 30FE. At the end of this instruction, data FE will be in register R. Data 30 will be in register H. Then RXI B 905A. Data 5A will be in register C. Then data 90 will be in register B. So in simple terms, if I use RXI D, for example, someone was using DE, not the BC, you will say RXI D 905A. Data 5A will be in register E. Data 90 will be in register D. So that from there now, because the question was asking us to add, so what do? We come here and look for an instruction which can add data in register pairs. We agreed in registers, we use add, maybe B, which meant add whatever is in A plus what's in B. But for register pairs, we use the instruction DAD. So we say DAD, double addition. That's the meaning basically. So whenever you see DAD, it implies double addition. Which register pair? B, C. So maybe if I put my arrows, it means whatever is in HR, add with what's in BC, the answer goes back to HR. So as we agreed, HR has become our accumulator, or that's where after the operation or after this arithmetic operation of addition of the 16-bit register data, it goes back to HR. Otherwise, because you're not told to store anywhere, we stop. Now, some candidates will not understand what we have done here unless and otherwise we write the trace table. So I want us to draw the trace table here so that at least you can see after each instruction execution what happens to different registers. So our registers here we are using is register B is inclusive, C is there, H and R. So I want us, at least if you don't understand the program, the trace table will assist you to do what? To understand what we are doing in each program. For example, here we say RXIH, so it is HR, not BC. So we put don't cares in BC because we don't know what's in B and what's in C. But what we know that in H we have 30 and there we have FE. So after at the end of the instruction RXIH30FE, it implies data 30 will go to register H, then data FE will go to register R. Then after that we say RXI B, now we are sure what's in BC. So here we have 90, here we have 5A, here we have 30, here we have FE. Now we are tracing what's happening after each instruction execution. The next is DAD B. It implies what? Whatever is in HR, add with what's in the BC, go back, the answer goes back to HR. So in simple terms, we have to understand digital electronics. If there is a carry, when we have a carry, we agreed a carry should be there when the result of an arithmetic operation is equal to or exceeds the base. And our base here is what? H, which means hexadecimal. So what will happen now is, I want to do it practically before I write there. That B means whatever is in HR plus what's in BC, the answer goes back to HR. So it is 905A plus 30FE. Now we want to add this. There are two ways, but I want to use the symbol as well. We have agreed that we are using base 16. So there should be a carry when the result of an operation exceeds what? Or equal to the base or the radix 16. So A is 10, E is 14. So 14 plus 10 should be 24, minus 16, the answer remains what? 8. Carry 1. The one we are carrying in this rectangle we agreed is equal to the base. 1 plus 5 is 6. 6 plus F, which is 15. So this is 21 sorry, that is 20 minus, let me see, 1 plus 5 is 6. 6 plus 15 is 21. 21 minus 16. The answer remains 5. So we have 5 here. Then here there is a carry. So because 0, 0, we have 1. 9 plus 3, it is 12. 12 in hexadecimal is what? C. So the answer here becomes C1 rather, sorry. The answer should be C1. C1 in H, because the answer goes back to HR. C158. But here we remain with 905A. Now, then next instruction is stop or halt. So when we stop, here we have 905A, C158. And this is our trace table. So I've used the trace table so that at least a candidate or somebody who want to understand this microprocessor Intel 885, we understand at each instruction execution what was happening. So at the end of the program, this is what's in register BC, and that is what's in register HR. And we agree this equation, we want to do it in two ways. The first way was using register pairs. The second way is using registers. Now let us move there so that now we do it what? Using registers. Remember the equation is addition of 3E F0H, then 905AH. We want to add these using registers. Because we don't know what the examiner would examine us, he might ask us using registers, pairs, or just using registers. Now, what we are supposed to understand and remember is in registers, a register can only take how many bits in 885? 8 bits only. So I know from from 0 to F, these are 8 bits. So I'm supposed to add this one first, put the result somewhere before I add again the other 8 bits. So in addition of 8 bits, in register pairs, HR is our accumulator. In 8 bits, accumulator is register A. So we start, the first instruction will be move immediate, MVI, A, F, 0H. Then MVI, the next general purpose registers, which we agreed, which was register B, what? 5AH. So already these 2 bytes of data, which are 8 bits, are in different registers, and we are supposed to sum them or add them. So the instruction will be add B, which means check what's in A, add with what's in register B. The answer goes back to A. Now, since I want to add 3E and 90, and the first summation or the first result of the first addition is in register A, I have to copy this data somewhere, because we said if you copy data, you remain with the original and a copy somewhere. So what I will do, I will come here and then I say MOV, copy MOV to another register. I can even decide to use C. Copy to the register C what is in A. So why am I copying? Because the candidate should understand why we are copying. We are copying, reason being, the result of the F0 plus 5A is in the accumulator. And the same accumulator is supposed to use to add 3E and 90. So the only option is for us to save this result somewhere, so that now we use A to add 3E and 90. So we come here and then we say move immediate, register A, 3E, then move immediate, register maybe E now. I can use D or any. I can even use again B, E90. So the data is in H, is in hexadecimal. So now before I add this, I have to check when I was adding this here, F0 and 5A, was there a carry? If there is a carry, then I should remember to add with an instruction which remembers a carry in the carry flag. Remember, when we are doing the flag register, we talked about several flags in the flag register. We talked about the carry flag, we talked about the auxiliary carry flag, we talked about the party flag, we talked about the sign flag and the 0 flag. So if there's a carry, we agreed that the carry flag would be set or would be at logic 1, indicating a carry has occurred. For example, 0 plus A is A, but F, which is 15 plus 5, is 20. So 20, if you now check here, 20 minus what? 20 minus 16 will be 5 carry 1. So now what happens here is, let us check. Let us check what will happen here. So I have to come here and say add with carry what? Register E. So it will check whether there was a carry here, and then remember the carry. So then here now we stop after doing that. Again, we draw the truth table to show what was happening in each instruction execution, so that at least candidates can understand. So we have register A, we have register B, we have register C, we have register E, and we have to remember the carry, because we have to indicate that during addition, if there is a carry, the carry flag will be affected. Where does that start? The trace table. The first instruction is move immediate A, F0. So we know that in A, we have F0. Here, we don't know what is there, so we put it on the case. Here, we put it on the case. Here, we put it on the case. Here, we don't know if there's something, so again, we put it on the case. Unless we are sure that a register has some data, don't put anything there. And we are not to put 0 because we don't know if somebody used these registers. So in digital electronics, or in microprocessor, we use don't case to indicate that we are not sure if there is data or there is no data. Then move B, 5A. Now we are sure in A we have F0, in B we have 5A, we don't know what's in C, we don't know what's in register E, and we don't know what's in the carry flag. Now, the next instruction is add B. What will happen? Add B means whatever is in A, which is F0, plus this 5A. So let us see. This one will be A. 5 plus 15, it is 20, minus 16 is 4. carry 1. So this 1 will go to the carry flag. So now we know what is in the carry flag. So the carry flag will be having what? Here now we have the result in A will be 4A, because now after addition, since we agreed that add B means whatever is in A plus what's in B, the answer goes back to A. So here we have 4A, here we have 5A. We don't know what's in C, we don't know what's in E, but we are sure that the carry now, there's a carry in the carry flag. So the moment the carry occurs, now what I want you to show to see as a candidate is the carry goes direct to the carry flag. Otherwise, copy the result from whatever is in A to C. Now we are sure in C we have something. Here we have 4A. In C we have also 4A. Here we have 5A. We don't know what is here, but we have the carry. Next instruction, move immediate, register A, 3E. So now we are sure here we have 3E. Here we have 5A. Here we have 4A. Here we don't know what is here. Here we have the carry. Next instruction, move immediate, E, 90. So here now we are sure that in A we have 3E. In B we have 5A. In C we copied 4A there. E now we are sure there is data which is what? 90. And then we have the carry in the carry flag. Now check the next instruction. It says what? Add with carry, register E. So it means this way. We check what's in A, which is 3E. We add what's in E, which is 90, and a carry in the carry flag, 3. So it will be 3E. I want to do it here so that you see it will be 3E in register A plus 90 in register E. So we get E, then C. And then we remember the carry flag. There's a carry in the carry flag, 0, 1. We get F, C. So the answer here now in A we have CF. Here we have 5A. Here we have 4A. Here we have 90. And since the carry, which was the carry flag, has been added, we remain with nothing in the carry flag. Now, when we stop, halt. So in A we have CF. Here we have 5A. Here we have 4A. Here we have 90. And here we have 00. So now this is our trace table of this program. So I've done it 2 ways. Using register pairs, this is the way, by using that instruction. Using registers, this is the way, by using add B. I hope that by the end of the exercise, a candidate who is supposed to sit for easy exams or high exams should understand that what's happening in this program. And once you understand these basics, even when you want to do what you call the program, which they call C, it will be easier for you to understand because now you have already the basics of programming. Now, what's remaining under this program, maybe we have not done, and we know to do today, is we need now to do what we call hand decoding or writing the hexadecimal machine code using the instruction set. So as we are proceeding, we shall see, or we shall use the instruction set to write what? Programs. Today I told you that we are doing several examples so that at least you can understand kumbe this microprocessor is easier and does not have what? A lot of difficulties the way people tend to think. So I want to do another example here, example 2, under microprocessor programming now. Example 2 is to do the following operation. Let me just reset my accumulator here. My accumulator is the board. So that now again we do another question. We see. So that at least before the lesson ends, at least somebody who is checking in our YouTube, it will be easy for her or for him to understand this program. So the second one now, I want us to do this, an operation which says 0F A 4 maybe H times 4. You write a program to do that. So write a program to do the operation of man 2, 0F AF times 4. Most of the time, the candidate sees, then they will start wondering, what are we supposed to do here? So I want to show you what happens. What we do already, we know that this data is 16 bits. So since it is 16 bits, we have to use what? Register pair. Now, our register pair which can be used for addition is register HL. So what we do, we come here and then we say RXI H 0F A4H. So I have initialized this data 16 bit to register H. Then I ask myself, I cannot multiply a 16-bit data by 2. What am I supposed to do? So I remember this instruction which is known as DAD, double addition. So I say DAD H, which means whatever is in HR, add with what's in HR, the answer goes back to HR. So I come here and then I say DAD H, DAD H. That's multiplied by 2. Our question was multiplied by 4. I DAD H again. DAD H. Then I stop. I alt. So, if you are a kid now, let me now try to show you what's happening. It is, I initialize this data 0F4 into register pair HR. That H in the bracket, let me put in the bracket so that people, yeah, but in the exam don't do that way. It means multiply the data in HR by 2. That H again, it means multiply the data here by now 4. Because if that H, it is HR plus HR times 2. Again, that H, now already what was in HR has changed. Like now, let me show you practically what's happening here. So we have 0F AF plus 0F AF. So here we have 8. This is 20 minus 16 should be 4, carry 1. Already this is remainder F, carry 1. That's the first one. So if you are keen, if you change the one to decimal and you multiply by 2, you can get this 1F48, which we can convert to decimal again. Then if you have a cross assembler. Then we have again a DAD H. Now this DAD H is this second one, which implies already HR has changed from 0FA4 to 1F48. Again DAD H. So what I want you to understand as a candidate, the first DAD H was 0FA4 plus 0FA4. But now already HR has changed to 1F48. So when we say DAD H here, it's not 0FA4 plus 0FA4. It's already changed to 1F48. So we are doing 1F48 plus 1F48. So basically this time is 2, and now this one is times 4. So we shall get 8 plus 8 is 16, 0, carry 1, 5, carry 1 here. This should be, let me see, this for 8, 8, 0, this 5, there's no carry. F plus F, that's 15 plus 15, that's 30 minus whatever it is, 14, which is E. Then carry 1, 3. So the answer is 3, E, F, 50, H. So what I want maybe someone to confirm, after you have checked our lesson and you have seen what we have done, after this, what you do, confirm if 3E50, you convert this one to decimal, you multiply by 4. Then you change the result into hexadecimal. You check if the answer is the same as 3E50. So by that way, now we can understand that we are multiplying the number by 4. I want to add one more example here. I want to do I've remembered another instruction which I need to introduce here so that people might not be suffering. What if it was the same number multiplied by 16? This same number multiplied by 16, now Roman 3, multiplied by 16, and store the results in memory locations. I want to add soup here. In memory locations, 6000 H and 6001 H. So we multiply this, the same 0F A4H times 16, and then we store the result in memory location 6000H and 6001H. Now, if you see that we have been given 2 memory locations, it means the result we are going to do is in 16 bits. And I think I will do this one. Then after doing this one, now, which means you could have understood something, I will stop. So the next one I will come again. I introduce more instructions. But I want to introduce a certain instruction here, which some people fear for no good reason. So what we do again, it is we understand the question now is I've done already 0.4 times 4. I want to show you 0f times 16. What am I supposed to do? So again, I say RXI H 0.4 RXI. Then we are multiplying by 16. Remember, we have agreed that H means multiply by 2. So what we do here now, we DAD H. DAD H. Then this by 2, dad h. By 4, dad h. By 8, dad h. By 16. So this by 2, in bracket, let me just put there so that when you are revising you can understand. This means 0fa4 times 2. This means by times 4. This means times 8. And this one means times 16. And then we look for an instruction which can take this result, which is in HR, to memory location 600 and 6001. And this one I will draw the trace table so that now people will understand clearly what's happening in each instruction execution. So now what will happen is I look for an instruction which can take 2 memory locations consecutively. So the instruction will be store HR direct 6000H. Otherwise, you stop. Most candidates, when they see this instruction, they tend to think that it's a very difficult instruction to understand. But what this instruction will do, it will add data in, it will store data in 16-bit data in 2 memory locations, starting with the lower byte, followed by the higher byte. The lower byte will be in register R, while the higher byte will be in register H. So whatever is in register R will go to memory location 6000. Whatever is in register H will go to memory location 6001. So if in case you see now the examiner will change to 5000 to 5001, the same program will run that way, but the difference will be now instead of 6000 we say store HR direct 5000. So before we stop, let us draw the trace table so that at least even if you do not understand, the trace table can enable one to understand correctly what was happening in each execution. So let us go. So let me draw here. We have register H, register R. We have memory location is 60000 and 60001. I don't know if we are going to get the carry flag, but let us continue. If we get that the carry flag will be affected, then we do the necessary. So what we do now, so that we don't we get the data correctly, we start now what's happening in each instruction. RXR H 0F A4. So HR will be affected. So it will be 0F A4. We don't know what is here, neither here we don't know what is there. Then that H, we agree that H means times 2, but let us do it now practically. It will be 0F A4 plus 0F A4. So here now we have 0. I want to reduce this byte to maybe to a smaller number so that maybe I don't get the carry. For our case, let us use something like 0, 2, A4. So let me use 2A, 2A. So even here I will change it to 2. So that now I don't complicate matters so that you start checking the carry flag. So let us continue now. 4 plus 4. So if this 4 plus 4, that is 8. A plus A is 10. 20 minus 16 will be 4. Carry 1, that is 5. 0. That's the first. Remember this times 2. That's how we agreed. Next now again is 0, 5, 4, 8. We add again, we add. We add. 8 plus 8 is 16, 0. Carry 1. 4 plus 4 is 8, 9. Nothing to carry. 5 plus 5 is A. Then this one is 0. This is, remember, times 4. Remember, it's multiplication by 16. So I'm supposed to be indicating after each what happens in HR. That H here now, HR changes to 0, 5, 4, 8. Still, you don't know what is here. Neither we don't know what is here. Next is, after that again, by 4, here we have now just from to that one from 2, 0A, 9, 0. We don't know what is here, and yet we don't know what is here. Then again, that H times 8. That H, 0A, that H. Add again. 0, 0 is 0. 9 plus 9 is 18. That's 2 carry 1. 1 plus 10 is 11 plus 10 is 20. That should be 5 carry 1. So the answer this now times 8 here. So here we have 1520. We don't know what is here, neither we don't know what is here. And then lastly, add H again. So it is 15 again plus 1520. So here we have 0, 4, A, 2. So now here we have 2A, 4, 0. We don't know what is here, neither we don't know what is here. So at the end of the program, this one should be seen as 2A. At the end of the program, after add 4 times, what's in A should be 2A. What's in H should be 2A. What's in register R should be 4, 0. And then we don't know what is there in these memory locations until we are going to be told to store HR direct. So before we end by store HR direct, I want to again during your own time convert this 202A4 into a decimal, then multiply by 16. Once you multiply by 16, convert back to hexadecimal, confirm if the result becomes what? 2A40. If it is that way, then now the program is able to do what? To run. So that difficult instruction people tend to think is difficult. I want to explain it using this example, which says store HR direct 6000. We agree this way. It stores data into 2 consecutive memory locations, starting with what's in R to 6000, and then what's in H to 6001. What's in R is 40. 40, it will go here. That's the memory location 6000. What's in H is 2A. We'll go to the next memory location. Then again, still, it will remain here 40. So once we stop, still H will be having 20. R will be having 40. This memory location, because we have stored, will be having 40, and then we have 2A here. And now, this is what the instruction will be doing in each execution. So I want to end by saying this way. The entire 885 microprocessor programming is not difficult. What is required by the candidate or by the lecturer who is teaching is to understand the instructions and then apply them in the writing the programs. Once you do this way, and then if you have the microprocessor set 888/885, you run the programs, you assemble them there, you execute them, then things will be cheap or will be easier to run. And if you have a question, you can put them in our YouTube, JEMSHAH. Once we see them, we shall tackle them so that at least at the end of the course or at the end of the day, at the end of the lessons, at least most of you have understood what's happening in microprocessor. Those who fear microprocessor, who tend to think the program is very hard, you have seen since we started with you here what we are doing. Things are simple so long as you understand the instructions and so long as you know where you apply them. When we shall meet next, we shall go to more instructions in 880/885, write more programs, do more calculations here and there, answer your questions if there is a question, so that at the end of the day, you have made it, you have understood, you can apply them, and then life will go what? Smoothly. Thank you so much for listening to me. Let us meet again next.